Everyone, and welcome. Today, we're jumping into a concept that's right at the heart of mechatronics and industrial automation. We're going to break down the language that tells these massive, powerful machines exactly what to do. So, yeah, let's get right into it.
Think about that for a second. What if you could control a whole assembly line? All the robots, all the conveyor belts, everything, just with a simple drawing. Sounds a little out there, right? Almost like science fiction. But believe it or not, that's pretty much what PLC programming lets us do. And it all came about because we needed to solve a really messy problem.
So, let's talk about that messy problem. To really get why PLCs, or programmable logic controllers, were such a game changer, you've got to picture what things were like before they existed. Imagine a factory floor, say 60 years back. The way they controlled machines, well, it was a total nightmare.
And this right here shows you everything you need to know. On the left, that's the before. See all those wires? That's a control cabinet packed with hundreds of physical switches called relays. Every single logical decision was hardwired. So if you needed to change just one tiny thing, an electrician had to come in and spend hours, maybe days, physically pulling wires and reconnecting everything. It was just a tangled mess, super expensive, incredibly slow, and a huge headache.
Right. The old way was just bad. It was slow, it was expensive, and it was so inflexible. Think about it. Every little change meant the entire line was shut down. A new product model? Well, that meant a massive, costly rewiring project. Industry was basically screaming for a smarter, more flexible way to run the show. And that brings us to the solution, the PLC. This little box is pretty much the hero of our story. It took all of that messy, physical, hardwired logic and crammed it into a single, rugged, and, this is the key part, programmable computer.
Now, when I say computer, don't picture the one on your desk. A PLC is built like a tank. It's made for the rough and tumble world of the factory floor. It can handle vibrations, crazy temperatures, tons of electrical noise, you name it. And through all that, it just reliably does its job, controlling everything from one tiny motor to a whole robotic assembly line. It basically replaced that whole cabinet of wires with a single, powerful brain.
Okay, so you've got this industrial brain. How do you talk to it? How do you give it instructions? Well, while there are a few programming languages out there, the big one, the one that's most common by far, is ladder logic.
All right, let's get into the good stuff. This is where it gets really cool. And I promise it's way more intuitive than you might think. We're going to break down how to read this language, and it's all about visualizing how logic flows, kind of like electricity moving through a circuit.
And they call it ladder logic because, well, it literally looks like a ladder. No clever metaphor here. You've got these two vertical lines called rails, which are like the sides of the ladder. And then, going across, you have the rungs. It's that simple.
So each one of those horizontal lines, each rung, is basically one line of your program. It represents a single piece of logic, a single instruction. The PLC just reads them one by one, from top to bottom, just like you'd read a list.
And here is the absolute golden rule of ladder logic. If you remember one thing today, make it this. Every single rung is just a simple if-then statement. If a certain condition is met, then an action happens. That's it. That's the core of everything we're doing here.
So let's look at the anatomy of a rung. It's always broken down the same way. On the left side, you have your conditions, your ifs. Stuff like if a button is pushed or if a sensor sees a box. Then on the right side, you have your actions, your thens. Things like then turn on this motor or then open that valve. Here's probably the best analogy, and it's one you use every day. An input, your condition on the left, is just like a light switch, and an output, your action on the right, is the light bulb. Simple, right? If you flip the light switch, then the light bulb turns on. That's a perfect one-rung ladder logic program right there.
Okay, so now we've got the pieces. Inputs on the left, outputs on the right, all arranged in these if-then rungs. But how does the PLC actually run the program? It's not like it just reads it once and is done. Nope, it's in an endless loop, checking everything over and over again at lightning speed.
And that loop has a name. The scan cycle. You can think of it as the heartbeat of the PLC. It's this continuous, three-step process that the PLC just repeats millions and millions of times to make sure it's always on top of what's happening and ready to follow your rules. So here's how that cycle works. It's always 3 steps. Step 1, read inputs. The PLC takes a look at every single switch and sensor that's connected to it and takes a snapshot of their status. Is this on? Is that off? Step 2, execute program. It then runs through your entire ladder program, from the top rung to the bottom, and figures out what should happen based on that input snapshot. And finally, step 3, update outputs. After it's solved all the logic, it turns all the motors, valves, and lights on or off. And then, it immediately goes right back to step 1 and does it all over again.
And this constant cycle, read, execute, update, is what makes the PLC's behavior what we call deterministic.
So, what does that fancy word mean? Deterministic just means it behaves in a super predictable and repeatable way. For the exact same set of inputs, you will get the exact same outputs every single time. And in industry, this isn't just nice to have, it's absolutely critical. You have to know that if a safety gate opens, the robot arm will stop, no questions asked. That kind of predictability is what keeps people safe and keeps products consistent. Now, of course, it's not all just simple on-off logic. Ladder logic has some special tools built in to handle more complex tasks. For example, you have timers, so you can create a rule like, if the tank is full, then wait for 10 seconds before you start mixing. You also have counters, which are super useful. You could say, if a package goes past this sensor, then add 1 to my count, and when that count hits 12, then stop the conveyor belt.
So here's the big takeaway. When you're programming in ladder logic, you're not just writing code. You're basically the choreographer of a mechanical dance. You are setting the exact rules, the precise sequence of events that this huge, powerful machine will follow over and over again perfectly every time.
So that brings us to the end, but I want to leave you with a little challenge. Think about a simple machine around you. It could be your garage door opener, a traffic light, even just your coffee maker. How would you describe what it does using only if-then rules? Give it a shot. It's a great way to start thinking like a PLC programmer. Thanks so much for tuning in.